So now we will study about real gas equation. Until now we have been studying about ideal gases. Now we are going to study about real gas. Okay. So for example, if you take this one, this is the equation of an ideal gas. Okay, ma? PV is equal to nRT. Okay. And how many ideal gases are there? Practically there are no ideal gases. But if temperatures are very high and if pressures are very low, then normal gases also they behave like ideal gases. So therefore, for ideal gas, this is the equation. PV is equal to nRT. So if I write this relation, PV divided by nRT, then it is equal to 1. Are you able to understand, ma? And this PV divided by nRT, this is called as Z, which is called as compressibility factor. Okay, ma? So this Z is called as compressibility factor. So if this Z, if it is, we can have two conditions here. So if Z is equal to 1, okay, ma, then the gas is an ideal gas. Okay. And when Z is not equal to 1, then it is a real gas. Is it clear, ma? So if Z is equal to 1, definitely I can call it as an ideal gas. But if Z value is not equal to 1, that is Z value may be greater than 1 or Z value may be less than 1, then in that condition, that gas I can call it as a real gas. Okay. So if Z value is greater than 1, are you able to understand? Then it means that, okay, ma, PV divided by nRT, it is also greater than 1. Z value is greater than 1, PV divided by nRT is also greater than 1. But here nRT, it is a constant, it is not varying. Only PV is variable in this condition. So if PV divided by nRT, if it is greater than 1 and nRT is a constant, then it also means that PV is greater than 1. This is what I can write. Okay, ma? So it means PV is greater. So therefore I can say PV is greater, it is larger. So if PV is greater, definitely I can say that in this condition, okay, ma, molar volume, it is definitely greater than 22.4 liters at STP. Okay, ma? What is meant by molar volume? Volume of 1 mole of a gas. Clear? So at STP, any ideal gas, it will occupy 22.4 liters of gas. 4 liters of volume. But in this condition, if Z is greater than 1, it means PV is greater, then I can say molar volume is definitely greater than 22.4 liters at standard temperature and pressure. Okay, ma? Whereas ideal gas exactly occupies 22.4 liters only. Okay. So therefore, if volume is greater, then also I can say that repulsive forces are dominant. This is what I can say. Okay, ma? So if repulsive forces are dominant, then only volume will be greater than 22.4 liters. Okay. See, in ideal gases, we considered that there are no what you call attractive forces, there are no repulsive forces. Okay. But for real gases, definitely there will be attractive forces also, there will be repulsive forces also. But sometimes repulsive forces will be dominating, sometimes attractive forces will be dominating. So in this condition, repulsive forces are dominant. Clear, no? Similarly, exactly opposite condition, how I can write if Z value is less than 1, definitely I can say PV divided by nRT is less than 1. Clear, no? And nRT is a constant, so therefore I can say that PV is smaller. If a PV is smaller, I can say that molar volume is less than 22.4 liters at standard temperature and pressure. Okay, ma? It means volume is reducing in this condition. If volume is reducing, it also means that repulsive forces are not dominant, but we can say attractive forces are dominant. Attractive forces are dominant in this condition. This is what I can write. Okay. So this is a small discussion on Z value, which is called as compressibility factor. Okay. Make a note up to here. Okay, ma? So then we study about the equation of a real gas, which was given by Vanderwalls. So therefore it is called as Vanderwalls equation of a real gas. Okay, ma? So this equation is written like this. So P plus n square V divided by A square multiplied by V minus NB is equal to nRT. Okay, ma? For how many moles of gas? For n moles of a gas. Clear? Similarly, for 1 mole of a gas, how can I write? I can write P plus V by A square. Okay, ma? So n square A by V square, ma. Okay. So P plus A divided by V square multiplied by V minus B is equals to nRT for how many moles of gas? For 1 mole of a gas. This is how I can write. Clear now? Then what is this A by V square? This is called as correction in pressure. Correction in pressure. And B is called as correction in volume. Okay, ma? So what is the reason that we are writing a correction factor for pressure? Reason is that, okay, ma? In real gases, there will be forces of attraction or forces of repulsion. So these forces, they tend to change the actual pressure which molecules should exert on the walls of the container if it is an ideal gas. Are you able to understand? So therefore, definitely pressure changes because of intermolecular forces. Okay. And similarly, what is the reason for we are writing a correction factor or correction term in terms of volume also? Okay. So in ideal gases, we assume that the molecules, they are having negligible size and negligible volume. Okay, ma? But actually, if a container is very small or if number of molecules, if they are very large, then definitely volume of the molecules also we have to consider. So therefore, the empty space is given by V minus B, where that empty space is the total volume of the container, and from that we are removing the volume of the molecules which are present. Okay. So therefore, a correction term means pressure is also present, a correction term in volume also we have to write down. Okay. Now in this equation, what does A represent? Okay, ma? What does this A represent? A represents force. Okay, ma? And force may be force of attraction also, or it may be force of repulsion also. But generally we take force of attraction. Generally we take force of attraction. Okay, ma? So generally, force of attraction is considered because maximum force of attraction will be present between the molecules. Okay. So therefore, also we can say that A is directly proportional to liquefaction of a gas. Okay, ma? It means if A value is greater, it means that that gas can be easily liquefied. How can you say that gas is easily liquefied? Because A is directly proportional to attraction. If attraction between the molecules is greater, then gas can be easily liquefied also. Clear? Similarly, what is meant by B here? Okay, ma? B is called as correction in volume. Okay. So therefore, B can be written as 4 multiplied by 4 by 3 pi r cube multiplied by Na for 1 mole of a gas. Okay, ma? Okay. Where 4 by 3 pi r cube is the volume of single atom or single molecule. Okay. And how many molecules are there? Na number of molecules will be present for 1 mole of a gas. And that I have to multiply by 4. Because this is how we derive the B value. So there is some derivation which we are not doing. So just you remember them. For example, if you say this is a molecule surrounded by many molecules, are you able to understand, ma? So consider this total volume. Then we have many empty spaces which are present here. Okay, ma? So all those empty spaces I can get only if I do this type of calculation. So B is equals to 4 into 4 by 3 pi r cube multiplied by Na. Where this 4 by 3 pi r cube is called as volume of single molecule. That is the formula. Okay. So what does B represents? B represents size of a molecule. Okay, ma? If B value is greater, it means size of that particular molecule is also greater. Okay. For example, if you write B value of oxygen is definitely less than B value of ozone. Clear? Because ozone is a bigger molecule when compared to O2 molecule. Okay. So that is what is represented by B here. So A represents forces which is responsible for change in pressure. B represents the correction in volume, and volume is because of volume of the gas molecules. Clear now? In real gases, volume of the gas molecules is negligible. We don't consider. But in real gases, and when volume of the container is very small, or number of molecules, gas molecules, if they are very large, then the size of the molecules also we have to consider. So therefore, correction term is B depending on volume of the gas molecules. Okay, ma? So this equation is called as the Vanderwalls equation for real gases. Okay. So make a note up to here. We will have some cases related to this one. Okay. Okay, ma? Now let us see what are the different cases we can study in the case of this real gas of Vanderwalls. Okay. Now let us see. Okay, ma? So first case which we study is if pressure is very low. Okay, ma? pressure is very low pressure. If pressure is very low, then volume should be very large, because nRT is a constant, no? Because nRT is a constant, if pressure is very low, volume should be very large. Okay, so therefore I can say volume is large. Okay, if volume is very large, so definitely you can remove this correction term here. Okay, because generally correction term will be very small, no? So if V is very large, B will be very small, so you can remove the correction term there. So therefore what I can write P plus A by V square multiplied by V is equal to RT. Okay, so we are removing the correction term in the case of volume. Now we will multiply this, so PV can be written as A by V is equal to RT. So divide everything by RT, so PV divided by RT plus A divided by V RT is equal to 1, and PV by RT is called Z compressibility factor, so Z is equals to 1 minus A by V RT. So this is the equation which I got. Clear, Nama? And by looking at this equation, definitely I can say that Z value is less than 1. Okay, ma? So here I can say that Z value is less than 1. So if Z value is less than 1, what is happening here? So definitely PV also will be lesser. So therefore I can say that volume reduces, and therefore here attractive forces are dominant. Attractive forces are dominant in this condition. Clear, Nama? So next we take one more condition. Second condition is if volume is very less. Okay, ma? If volume is very less, it means pressure is very large. So if pressure is very large, you can remove the correction term which is present. So therefore I will write P multiplied by V minus B is equal to nRT. Clear, Nama? So therefore PV minus PB is equal to nRT. So therefore PV divided by nRT minus PB divided by nRT. Okay, ma? So this is equal to 1. This is the relation which I can write. Are you able to understand? Okay. So number of moles is 1 only, Nama. No need of writing nRT here. Just you can write RT in this condition. Okay. So therefore PV by RT is nothing but what? It is nothing but Z. So Z minus PB divided by RT. So this is equals to 1. So therefore what is Z value? Z value is equals to 1 plus PB divided by RT. Are you able to understand? So this is the equation which we got. Now by looking at this equation, I can say that Z is definitely greater than 1, because here we have 1 plus PB by RT, no? Clear, Nama? It means definitely Z value is greater than 1. Okay, ma? So if Z value is greater than 1, it means which forces are dominant here? I can definitely say that repulsive forces are dominant in this condition. Okay, ma? So repulsive forces are more dominant in this condition. Okay. Similarly, I can study one more case, ma. One more case is that pressure is less and temperature is very large. Okay, so this is a condition. So I hope you remember this condition. This is a condition where any gas behaves like an ideal gas. Okay, so therefore pressure is less and temperature is very large. Okay, see, if temperature is very large, okay, if temperature is very large, then what I can say, the gas molecules, they have very high velocity. Their kinetic energy will be very large, their velocity will be very large. Okay, and if velocity is very large, so the attractive forces and repulsive forces, they play a very small role. Almost they play no role. So therefore you need not write the correction term in the case of pressure. So what is the reason for writing the correction term in the case of pressure? Only attractive forces and repulsive forces were responsible. Okay, so therefore I can say if temperature is very large, okay, ma, then forces does not play any role here. Okay, so therefore I can write you can remove the correction term in pressure. Remove correction in pressure. Okay, ma? Similarly, we are also saying that pressure is very less. Pressure can be very less only when volume is very large. Okay, so therefore again you can remove the correction term in the case of volume. Okay, if you remove the correction term in the case of volume, then what is the equation I will get? I will get PV is equals to nRT. This is the equation which I guess, and this is definitely the equation of an ideal gas. Okay, ma? So all these conditions you are supposed to remember very carefully, ma, because previously many questions were asked on these concepts in previous NEET and mains examinations. Okay, make a note.